Okay, hello, welcome to Equity Education, the chemistry version, and today we're going to be looking at electrochemical cells and electrode potentials. Okay, so if you could open up your booklet, we will go on and get started. Oh, just before we do, you'll have to do some calculations, and the electrode potentials are at the back of this booklet that you'll need to use. Okay, so right, so electrochemical cells. So what are they? Electrochemical cells are two half cells that are joined together. They must have a salt bridge and a potential difference will be produced if they're connected into a circuit. This can be measured by, unsurprisingly, a voltmeter. Okay, so if we go down here, this is an example of two electrochemical cells, an electrochemical cell. So this one on this side is a half cell, this on this one is a half cell as well. And because we have potential difference, it will create a potential difference to produce an electrochemical cell, and we can measure it by a voltmeter. So we need to add some labels to this. So unsurprisingly, up here, this is our voltmeter. This is our salt bridge. This is a zinc electrode. This is a copper electrode, and then we need some solutions as well. So this solution contains aqueous zinc ions, and this solution contains aqueous copper ions. Okay, so, and we also need to say that this is my negative electrode and this is my positive electrode, and my electron flow is going from left to right. Okay, and really, yes, we'll stick them on. So my concentrations, we'll do this later as well, but we need to get used to it. My solutions are 1 mole, Dm minus 3, and we have an overall temperature of 298 K. Okay, so we'll talk about what's going on here. So a zinc cell has more tendency to oxidize and release electrons, which means that this half cell becomes the cathode, so the negatively charged, which we can see here that we've labelled. So that means in this half cell, the zinc electrode is oxidizing to produce Zn2+, which is in the solution, and 2E-. Okay, so what's happened at the copper side? So at the, so the electrons flow into the copper half cell, and the copper ions from the solution gain the electrons to form solid copper, and the copper half cell is the anode, positively charged. Okay, so what this means is that the copper ions from my solution are going to gain electrons to form solid copper. And if we go up, we can see this happening. So in the left hand side of my half cell, in the zinc half cell, the electrons are forming, we're gaining electrons on the zinc electrode, and then these electrodes are going through this circuit into my copper, and the Cu2 plus in solution gains these electrons, gains these electrons from the electrode to form solid copper. So we get this. So we get this half equation. So that means that, as we just said, a potential difference is created between the two electrodes. This is measured using a voltmeter. And we call this, and it is called the electrode potential of a cell, and it's usually labelled as E cell, and that's what we're going to measure today. Okay, that makes sense. I assume you've done electrolysis before. It basically is electrolysis. Okay, so moving on. So, what's this salt bridge? What does the salt bridge do? So the salt bridge connects the circuit through the transfer of free moving ions in the solutions, in the two solutions. And we usually make a salt bridge, is usually made from filter paper soaked in a salt solution, such as potassium nitrate, KNO3. And the salt solution must be unreactive in the electrochemical cell. So the salt bridge is really, really important. If we go up and look at our diagram, so the salt bridge connects these two half cells, and it allows for the movement of ions between these cells. And without this, the circuit wouldn't be complete, and we wouldn't be able to gain this potential difference. Okay, so standard notation of electrochemical cell. Depending on your board, you might need to know this, you might not. It's always very useful because it usually appears in textbooks anyway. So if you are writing standard notation of electrochemical cell, you don't have to draw it all the time. Sometimes you can just write it. We would have, for our diagram, okay, so this would be our standard notation. So let's have a look and see if you can work out what all these things are. I'll give you a minute, just have a think about it. Refer back to the diagram, see if you can work it out. Okay. Okay, so see how we got on. So our Zn, our zinc, shows our electrode, and our Zn2 plus, so it's our solution. This double line is our salt bridge, again solution and electrode. And if we go up, we can define this a little bit more, so we can say that this is the cathode. And this is our anode. In general, when you're drawing electrochemical cells, we always try and put the cathode on the left and the anode on the right. Okay, but if you do it the other way around, it doesn't really matter that much. And in this example, because we have done the cathode to the anode, the electrons flow from left to right. So these are useful if you can't be bothered to draw out, or books you see in books and they can't be bothered to draw out electrochemical cell. You can understand what is going on in this actual cell. Right, so next bit. Right, so in general, electrochemical cell will be made from, if it is a metal, we will need a solution containing the metal, an electrode made from the metal. But this is only if the solution contains 2 or more ions. Then we use a platinum carbon electrode. But in general, when you're looking at these electrochemical cells, it's usually just one metal that you're measuring, which has one ion involved. So it will be that metal, but just be aware. Okay, we also need a salt bridge and a voltmeter, and all solutions at 1 mole DM-3, temperature at 298 Kelvin. Okay, so when you're in the exam, you have to draw these electrochemical cells and you have to include all of these details. A lot of students miss something out and they're silly marks to miss out. Okay, so if there is a gas involved, we would need a solution containing the ion of the gas. So for example, if we had chlorine gas, we would have a solution which contains Cl-, aqueous Cl-. An electrode made from platinum a salt bridge and a voltmeter. All solutions, unsurprisingly, at 1 mole DM-3. All gases at a pressure of 100 kilopascals and temperature of 298 K. But you might have noticed that these are our standard conditions, and we always try and measure using these standard conditions, so we have cell potentials that are equivalent to each other. Okay, so moving on. Standard hydrogen electrodes. Okay, so to measure the electrode potential, which we give the value of E of a half cell. This is what we use. We use the standard hydrogen electrode. The half cell in question is measured against the standard hydrogen electrode, which is usually shortened to She, and the She is given the cell potential of 0.00 volts under standard conditions. We'll write them again. So concentrations of solutions at 1 mole DM-3, pressure of gas at 100 kPa, kilopascals, and temperature of 298 Kelvin. So we're measuring other half cells against our standard hydrogen electrode, and we give it an arbitrary value of 0.00 volts, and then we can measure all of our different half cells against this standard. Okay, so by connecting a half cell to a standard hydrogen electrode, we can work out the strength of the oxidizability of the half cell. This is called the electrode potential, and it is always shown as a reduction half equation. Okay, so if we just skip to the very end, I'll show you a quick example of these. So let's have a look. Oh, I forgot to mention it's quite long, this one. So here are our reduction half equations, yeah, and we can see that it's always shown as a reduction equation, and here are our cell potentials. Okay, so it can be positive or it can be negative, and we'll talk about what that means in a little bit. Right, so gotta go all the way back up. Okay, so drawing a diagram of measuring a cell potential using standard hydrogen electrodes. Okay, so I just have let you have a look at this, and drawing the electrochemical cells, see what you think you must include, as we've been through quite a bit of this already. So just have a think about what this diagram is and how we're going to label it. Okay, be back in a second. Okay, right, so you definitely should be able to label some of these things. So we definitely need a salt bridge, so we know this must be salt bridge. This must be my voltmeter. Oh, I didn't say what this is. Right, so this looks like copper. If you've got a coloured printed version of this, so this is copper, which means this must be my copper ions solution, and over here must be my standard hydrogen electrode, which means I have hydrogen gas going in here, and I have a solution of H+ ions. Now this is a gas, so that means that my electrode must be platinum. And the other thing I need to do is write on my standard conditions. So my gas would be at 100 kilopascals. My solutions are at 1 mole DM-3. And I have a temperature of 298 K. Right, is there anything I have missed? I don't think so. Okay, yeah. So there is an example of a standard hydrogen electrode measuring an electrochemical cell with a standard hydrogen electrode measuring the cell potential of another species. In this case, it's copper. Okay, so drawing electrochemical cells, what do we need to include? Well, we need salt bridge, we need a voltmeter, we need to label standard conditions, we need labeled electrodes, labeled solutions, and labeled gases. Okay, and as I said before, people always forget to do these or forget one of these, and it's really silly because it's just a loss of marks in the exam. Yeah, so I know we've been writing it quite a lot. I'm going to still get you to write it so you can remember them. Okay, so moving on. So using E-values to predict cell voltages. And these are standard E-values, so it should be a standard here. So electrode potentials can show the direction of spontaneous change in a redox reaction. So electrode potentials are always written as their ability to be reduced. Hence their ability to act as an oxidizing agent. Okay, now remember, oxidizing agent is the ability of a species to oxidize something else while itself gets reduced. Okay, so moving on. I'm going to write down 2 examples from my data at the back of this booklet. So Mg2 plus 2E minus goes to Mg solid, and this has a potential value of minus 2.37 volts, and Cu2 plus Aq plus 2E minus forms Cus. Whoops, it's not very good, E, which has a value of plus 0.34 volts. Okay, so thing we have to do when we're trying to work out which way this chemical equation will go, will the magnesium get reduced or will the copper get reduced? Okay, so we're forming a redox equation, which you should be familiar with. So for any 2 half equations, the more negative half cell will always oxidize. So in this example, it's my magnesium. So I can take my magnesium now, and change it to an oxidation reaction. E.g., so my solid magnesium will lose 2 electrons to produce Mg2+. And the more positive half cell will always reduce, unsurprisingly, which means that my copper half cell will be reduced because it has the most positive E cell potential. Okay, so I can now add these together as long as our electrons cancel out, which they do. You should know this from our redox session. And we can make the overall equation as Mgs plus Cu2 plus Aq forms Cu solid plus Mg2 plus Aq. Okay, simple so far. Okay, and we can work out the overall E potential E cell by using this equation. So E cell equals E reduction minus E oxidation. So my potential values for the reduction equation and the potential minus the potential of the oxidation. So we decided that copper is being reduced, so that is 0.34 plus 0.34 minus 2.37, is that correct? Let's check. Yes, minus 2.37, which gives me a value of plus 2.71 volts. Okay, so this tells me the cell voltage is plus 2.71 if I connect these 2 half cells together. The positive sign of the E cell shows that it is a feasible reaction or is spontaneous, so it will happen. Right, hope that makes sense. I think it's quite straightforward. All you have to remember is this equation, and you should be able to work out these cell potentials. So, your turn. Okay, so have a go at answering these questions, and I'll be back in a minute. Okay. Just noticed I haven't actually given you any questions, so let's write them on. So the first one is, that was clever, Zn2 plus 2E minus goes to Zn, Cl2 plus 2E minus goes to 2Cl minus. Okay. My second one. It'd be good if you could work them out without giving you any clues. Zn and Fe2 plus 2E minus goes to Fe, and lastly Cu2 plus 2E minus gives you Cu, and Ni2 plus 2E minus gives me Ni. Okay, so I'm not going to give you the cell potential values. You're going to have to look at your data booklet to work these out. Right, let's try again. I'll give you a couple of minutes to work these out. Okay, so let's have a go at going through these. Hope you managed to answer them. I'm pretty sure you did. So first one, we have Zn2 plus and Cl2, and our negative one will be oxidized, so that means it's my zinc. So I will change this to zinc S forms Zn2 plus Q plus 2E minus. I can now add them together because my electrons cancel out. Remember to include your state symbols in the overall equation. I didn't here, that was me being naughty. So ZnS plus Cl2 gas forms Zn2 plus Aq plus 2Cl minus gas, and I can work out my E cell equals reduction minus oxidation, therefore plus 1.36 minus 0.76, which gives me a value of, what does it give me a value of? Plus 2.12 volts. Okay, moving on. Again, I've got Zn, which is minus 0.76, and I have Fe2 plus, which is minus 0.44. So we have the most negative will still be oxidized, which again is my Zn. So I change this to my oxidation, and now I can write the full equation. So Fe2 plus Aq plus Zn solid forms Zn2 plus Aq plus Fe solid. E cell is my reduction minus my E oxidation, which is minus 0.44 minus 0.76, which gives me a value of something. What does it give me a value of? Plus 0.32 volts. And lastly, my most negative is nickel. So this will become my oxidation equation. I can now add these two together. So Cu2 plus Aq plus Ni solid forms, oops, 2 plus up here, Ni2 plus Aq plus Cu solid. My electrons cancel out, so I don't have to do anything with balancing. Again, E cell equals E reduction minus E oxidation, which would be 0.34 minus 0.26, which gives me a value of plus 0.6 volts. Okay, right, so pretty self-explanatory, I think. I think everyone will be able to work them out. So it's your turn again now. So let's see if I've actually given you enough information for this. Draw the electrochemical cell for question 1 and complete the standard notation. Right, okay, yes I have. Okay, so have a go at this, and when I come back I will go through the answer with you. Okay? Okay, right, so I quickly draw my outline. It doesn't obviously have to be a work of art, mine definitely isn't, yeah, as long as it's pretty clear. And now we're going to label it. Okay, so you should have labelled it as, so this would be my salt bridge. This is my voltmeter. On this side is my oxidation, so this is my zinc. We're using zinc? Yes we are, which means this must be my solution containing zinc ions. What else do I need? Whoops, I'm not doing a standard electrode. We are doing Cl gas, which goes in here, which means my solution must be Cl minus. And because we're using a gas, this must be a platinum electrode. And then we need to write on our standard conditions. (100 kPa) at 298 Kelvin. Have I forgotten anything? No, don't think so. Got my state symbols. Yeah, so you've got everything. So yours should look something like mine. It may look slightly neater, may not. It doesn't matter as long as it's labelled correctly and you can read it. Okay, and draw the standard notation. So we always try and stick, again, as I said, that negative on this side, so that would be my zinc electrode, and my solution, my salt bridge, my solution, and my electrode. So this is what my standard notation should look like. And a quick note just before we move on, sometimes you may see in the solutions here, for example, other ions as well. So you may see it as Zn and SO4 2 minus, whoops, 2 minus. Okay, so this is just what the solution is made of. So this example would be zinc sulfate. Don't worry about this too much, but if you look in books and you see a negative ion, it's because that's what the solution actually is. We're just listing the important ions that are involved during this reaction. Okay, so what are we going to do now? So using standard electrode potentials to predict redox reactions. Okay, so if the overall voltage of the electrochemical cell is positive, then the reaction is feasible. If the overall voltage of the electrochemical cell is negative, then the reaction is not feasible. Okay, so in our previous examples, when we were working out the potential of the E cell, they're all positive because they're all spontaneous reactions, they're all feasible reactions. Now we're seeing if we're now trying to predict whether a reaction is feasible or not using standard electrode potentials. Okay, so can bromine oxidize silver metal to Ag+? I will do this together and we will do this together and then you can have a go at the last one. So the first thing I need to do is write down my two reduction equations. So bromine, Br2 plus 2E minus forms 2Br minus Aq. Have a look in your data booklet at the back and you will find out that we have a value of plus 1.09 volts. And can bromine oxidize silver metal to Ag+? So I will write it quickly the right way around. Ag solid, Ag AQ. We need to balance this. No, we don't need to balance it because we're only working out. We don't have to do the overall equation. So in the question it says, can bromine oxidize silver metal to Ag plus ions? So that means that what would be happening is my Ag would be oxidized to my ions. And I've forgotten my E value for this would be 0.8 volts. Okay, so I can now use my equation. By reduction minus oxidation. So my reduction equation, according to the question, is my bromine, so 1.09, and my oxidation is my silver, so 0.8, which gives me a value of plus 0.29 volts. Okay, so because it's positive, yes, this reaction can happen and is feasible. Hope that makes sense. Yep, so you have to read the question and do what the question asks, unlike in our other examples we were going through earlier. Okay, so let's have a go at the next question. So can iodine oxidize silver metal to Ag plus ions? Okay, I'll give you 5 minutes. Okay, so I've just written these out. I'm sure you have as well. So these are my two reduction equations. I need to turn the bottom one into an oxidation because that's what the question asks me. So silver being oxidized, use my ions, plus E minus. Okay, so according to this reaction, according to the question, the iodine should be reduced and the silver oxidized to the Ag plus ions. I put these values in here, so my reduction would be 0.54 minus 0.8, which gives me a value of 0.26 volts. So this is a negative value here, so that means that this reaction will not occur spontaneously or is not feasible under these conditions. Okay, hope that makes sense. So we've done two different examples. One where we're just working out the E cell potential, and one where you were working out the spontaneity or the feasibility of a reaction. Right, so what are we going to go on to now? So, okay, limitations of the standard electrode potential approach. So all electrode potentials are measured under standard conditions. In reality, experiments are not always carried out under standard conditions. We're in a lab. It's quite difficult. So changing concentrations affects the E value. So increasing the concentration of, for example, okay, no, let's just write it to begin with. So if we look at this equation, Fe3 plus E minus goes to Fe2 plus AQ, and plus 0.77 volts. Okay, so we should be able to work this out together. So increasing the concentration of Fe3 plus will make the E value more positive in this example. I must put or less negative depending on what the example is. This is because of Le Chatelet's principle, as the equilibrium will shift to the right. Oops. Therefore, increasing concentration of Fe2 plus and increasing the E value. Okay, so because we have shifted this equilibrium, so we have increased the concentration of my Fe3 plus, which has shifted the equilibrium to the right. This will increase my concentration of Fe2 plus on this side to minimize the change in concentration over here. As we go from left to right, it means that my E standard value will increase. And that means that if we don't perform these experiments under standard conditions, then occasionally you get reactions which can occur, but they don't necessarily under standard conditions, and it's to do with the concentrations usually. Okay, so we can have a look at a bit of reaction rates as well. So a feasible reaction may occur according to E values, however the rate of reaction may be unsatisfactory because, as always, when we look at these examples, the activation energy is too high. And a change in temperature could also affect the E values, could also affect the E value due to the Chatelier's principle. However, this is less of a factor, and that's because these reactions might be exothermic or endothermic, and if they are exothermic and endothermic, then obviously it will affect the position of the equilibrium. But this doesn't really affect the overall cell potential as much as changes in concentration. Okay, so I think we're going to have a quick break here, and I'll be back in a second before we go on to storage and fuel cells. If you want to stop here, that's fine. We've done quite a lot of work. Storage and fuel cells is basically just a lot of remembering. Okay, I am going to get you to work some things out, but really you just need to remember it. Okay, so be back in a minute. Right, okay, so we will carry on. So storage and fuel cells. So as I've just said, you do not have to remember any construction of fuel cells, only how to calculate the E cell or occasionally the overall equation. So we've got two different types, so storage cells and fuel cells. So storage cells are used to supply electricity in many applications such as shavers. They are generally rechargeable. Cells, an example is the nickel cadmium cell. I haven't given you a diagram because you don't need to know what's happening. However, I would like you to have a go at trying to construct the overall equation and calculate the E cell for the nickel cadmium cell. Okay, remember it's got to be positive, yeah? So I will just write down the two equations and then it's over to you. Okay, so these are my two equations and I've given you the standard potential E values. So have a go at completing this overall equation and calculating the E cell value. Okay, so the first thing we need to do is work out which is going to be reduced and which is going to be oxidized. So the most positive will be reduced and the least positive or most negative will be oxidized. So my cadmium half equation is going to be oxidized, so I need to change that around. So I would have Cd plus 2OH minus Q plus Cd OH2 Q. Whoops. You did it better than me. Plus 2E minus. Is that correct? So Cd plus 2OH minus goes to Cd cadmium hydroxide plus 2E minus. Yes. Okay. Now you might also notice that our electrons don't balance, so I need to make sure that I balance this equation, and now I can add these together. So I will get 2Ni OH plus 2H2O. It's going to be a long one. Oh, just when I'm doing this, should be 2 electrons here. Plus Cd plus 2OH minus goes to 2NiOH2 plus 2OH minus plus CdOH2. And is that it? I think it is. I'm not going to write the state symbols in just yet because we're going to make sure we're going to see if we've got species which are on both sides, which we do. We have 2 hydroxides and 2 hydroxides, so we cancel them out. So our overall equation should be H2O plus Cd 2Ni OH2 plus CdOH2. I can then go back and write my state symbols in. So aqueous, liquid, solid, aqueous, aqueous. Just check to make sure it balances. CdOH2, I think it does balance. And now we can work out the E cell of the potential of the cell using reduction minus oxidation, which gives me a value of 0.52 minus 0.88, which gives me a value of plus 1.40 volts. Okay, so the reason why I got you to do that is to just get used to using these redox equations. I know you've done them in a previous video, however it's always good to practice. Okay, so I hope you got that correct, and now we can move on to hydrogen fuel cells. So a fuel cell produces electrical power from a chemical reaction of a fuel with oxygen, e.g. let's do hydrogen or I don't know, methanol. An example of the fuel cell is the hydrogen fuel cell. Okay, so basically what we have is a fuel and we react it with oxygen to produce electrical power, and it's through a chemical reaction. Okay, and in this example, the electrodes are made from titanium sponge coated in platinum, usually because we involve a gas, so we have the platinum electrode. The electrolyte So our solution containing the ions is alkaline or acidic membrane that allows ions to move from one part to the other. So this membrane acts a bit like the salt bridge in the examples that we have done. So am I going to get you to do this? I'm just going to have a think about it, and then we can either go through it together, or if I'm being mean, make you do it. Okay? Okay, yeah, I am going to be mean. So I've written these down for you, and what I want you to do is to construct the overall equation and work out the E cell for this hydrogen fuel cell in alkaline conditions. Okay, and then we'll do the acidic one afterwards. Okay, so I'll give you 5 minutes. Okay, so I hope you managed to do this, so we'll go through the answer. Right, so as we've been talking about, the positive one will stay as my reduction, and the negative one, or the most negative, will be flipped for my oxidation. So I flipped my second equation for Hc plus 2OH minus 2H2 plus 2E minus. That's my oxidation. I can now add this equation to my top one. Let's see if I can get it right. So half O2 plus H2O plus H2 plus 2OH minus forms 2OH minus plus 2H2O. I'm not going to write the state sums in just yet, because you may notice that I can cancel some of these out. Can I cancel anything else out? Yes, I can cancel this out, and this will become 1. So my overall equation will be half O2 plus H2 goes to H2O, gas, gas, liquid. Then I can calculate my cell potential, which will be plus 0.4 minus 0.83, which gives me a value of something plus 1.23 volts. Okay, straightforward. Yeah. So you may be asked to work this out. Usually it's not. It's usually in exams. It's not quite as difficult as I made it out for you, but it's always good practice. Okay, so I know this is a long one, but we are nearly done. We are nearly done. So in acidic conditions, I'm going to write this down, and then guess what? I'm going to make you do it again. So plus 2E minus goes to H2 gas, which has a value of 0.00 volts. I don't know why I was looking at that. You can tell me why I was being stupid then in a second. And what's our other equation? Is half O2 gas plus 2H plus Q plus 2E minus goes to, this is a standard equation, H2 now plus 1.23 volts. You may be laughing at me trying to find out what the top equation was and what the cell potential was, and well, that's obviously the standard hydrogen electrode, so it's given the value of 0.00 volts. Right, so same as before, calculate the overall equation and calculate the E cell. Right, so my least positive turns into my oxidation, so I need to flip around the top equation, H2 gas goes to 2H plus 2E minus. I can now add this equation with this equation because my electrons will cancel out. So half O2 plus 2H plus H2 forms plus H2O. I can cancel these two out. I just realised I've left you space, so I'll have to copy it back down here. So my overall equation would be half O2 plus H2 gas goes to H2O liquid. And lastly, we'll write this quite big because this is the last time you're going to have to calculate it. My reduction value is 1.23 and this is my standard hydrogen electrode, so minus 0.00. So it forms plus 1.23 volts. And you may realise or have noticed that the E cell for in acidic conditions and alkaline conditions is exactly the same. And that's not surprising because the overall chemical reaction is also exactly the same. Right, so we are really nearly done now. The last thing we need to do is advantages of fuel cells. Again, you just got to learn this. Right, so I'm just going to write them down. So advantages of fuel cells, especially when we're talking about the hydrogen fuel cell, is it's less pollution. So if we're reacting hydrogen with oxygen, we're just going to have water produced. And it has a greater efficiency compared to normal generations of electrical power. Disadvantage of fuel cells are storing the hydrogen in particular and transporting it. And it's expensive and dangerous, yeah, because it's a flammable gas. It's got to be transported under high pressure, which makes it more dangerous. So there will be more stringent safety rules, which makes it more expensive. And there's also a limited lifetime and high production costs. And there is also use of toxic chemicals in their production. Again, I don't want to go into too much detail about this because you may be asked about some advantages or disadvantages. You've just got to remember them. Okay, so I know that's been a long one. I hope you've stuck with me and I hope you found it useful, and I will see you next time. Okay, bye bye.